Hello, today we will prove the chain rule very slowly, one line at a time. We will follow one clear order. First, convert u into a function of t. Second, use the definition of the derivative. Third, add and subtract one helpful term. Then the answer will arise naturally. We are given u equals f of x comma y, but x itself is phi of t and y itself is psi of t. So, when t changes, x changes, y changes, and finally u changes. Our target is the rate of change of u with respect to t at the point t. The formula shown in green is what we must prove. This is the first and most important step. In u equals f of x comma y, replace x by phi of t and replace y by psi of t. We obtain u of t equals f of phi of t comma psi of t. Now u has been converted into a function of the single variable t. Therefore, we can apply the ordinary definition of a derivative. By definition, du by dt at the point t is the limit, as delta t tends to 0, of u of t plus delta t minus u of t divided by delta t. The numerator is the change produced in u. The denominator is the small change made in t. The limit gives the change in u per unit change in t at that point. What is u of t plus delta t? In the composite expression, replace every t by t plus delta t. So it becomes f of phi of t plus delta t, comma, psi of t plus delta t. At the original point, u of t is f of phi of t, comma, psi of t. These are the two function values required by the derivative definition. Now substitute those two values into the derivative definition. Nothing new has been assumed. We have only written u of t plus delta t and u of t in terms of f. The numerator now shows the total change in f caused by the small change delta t. But this expression is long, so our next demand is to write it more clearly. Let x mean phi of t and let y mean psi of t. When t changes to t plus delta t, the change in x is phi of t plus delta t minus phi of t. We call this delta x. In exactly the same way, the change in y is psi of t plus delta t minus psi of t. We call this delta y. From the definition of delta x, phi of t plus delta t equals phi of t plus delta x. Since phi of t is x, this becomes x plus delta x. Similarly, psi of t plus delta t becomes y plus delta y. This is only the familiar idea: the old value plus its change equals the new value. Use x plus delta x for the new x value and y plus delta y for the new y value. The derivative quotient becomes f of x plus delta x, comma y plus delta y, minus f of x comma y, all divided by delta t. Notice the difficulty. In this numerator, x and y are changing together. Our target contains partial derivatives, but a partial derivative changes only one variable while keeping the other variable fixed. The present numerator changes x and y together. Therefore, it demands a separation. We first move from x comma y to x comma y plus delta y. Then we move to x plus delta x comma y plus delta y. The middle point is the key. The middle function value is f of x comma y plus delta y. Add it and subtract it in the numerator. Because the same quantity is added and subtracted, their net effect is 0. So the original value has not changed. But the total change has now been separated into an x part and a y part. Now divide each piece by delta t. Look at the first fraction. Both function values contain exactly the same y value, y plus delta y. Only x changes from x to x plus delta x. Look at the second fraction. Both function values contain exactly the same x. Only y changes from y to y plus delta y. This is the separation we needed. In the first piece, we need a change in x in the denominator. So divide and multiply by delta x. The first factor is now a difference quotient with respect to x. Inside this factor, y plus delta y is exactly the same in both function values, so it is fixed while x changes. The second factor is delta x divided by delta t. Do the same thing with the second piece. Divide and multiply by delta y. The first factor is now a difference quotient with respect to y. Here x is exactly the same in both function values, so x is fixed while y changes. The remaining factor is delta y divided by delta t. Put the two prepared pieces together. We now have four factors. The first is an x difference quotient. The second is the rate of change of x with respect to t. The third is a y difference quotient. The fourth is the rate of change of y with respect to t. Now the expression is ready for the limit. Before taking the limits, let us prove every step. First, why does delta t tend to 0? It tends to 0 because du by dt is defined as the limit of the change in u divided by delta t, as delta t tends to 0. We deliberately make the change in t approach 0 in order to obtain the instantaneous rate at the point t. Now we must prove that this forces delta x and delta y to approach 0. Start with the definition of delta x. Delta x equals phi of t plus delta t minus phi of t. For non-zero delta t, divide and multiply this expression by delta t. Then delta x equals the difference quotient, phi of t plus delta t minus phi of t divided by delta t multiplied by delta t. This equality is the key to the proof. Take the limit as delta t tends to 0. The limit of a product is the product of the two limits. The first limit is phi prime of t because it is the derivative definition of x equals phi of t. This derivative is finite because x is differentiable. The second limit is 0 because delta t tends to 0. Therefore, the limit of delta x is phi prime of t multiplied by 0, which equals 0. Hence, delta x tends to 0. Now prove the same result for y. Delta y equals psi of t plus delta t minus psi of t. For non-zero delta t, divide and multiply by delta t. Thus delta y equals the difference quotient for psi multiplied by delta t. We have again converted the increment into a derivative quotient multiplied by the small change delta t. Take the limit as delta t tends to 0. The first factor tends to psi prime of t by the derivative definition of y equals psi of t. The second factor tends to 0. Therefore, the limit of delta y is psi prime of t multiplied by 0, which is 0. Hence, delta y also tends to 0. We have now proved the statement, rather than merely assuming it. When delta t tends to 0, delta x tends to 0, and delta y tends to 0. The reason is that x of t and y of t are differentiable, so each increment is a finite derivative quotient multiplied by delta t. This is also the direct proof that differentiability of x and y implies their continuity at t. Now we may safely evaluate the partial derivative limits. Consider the first quotient carefully. For each small delta t, y plus delta y is fixed inside the quotient, while x changes by delta x, so it is an x-direction difference quotient. As delta t tends to 0, delta x tends to 0, and y plus delta y tends to y. Because the partial derivative f sub x is continuous, this quotient tends to partial f by partial x at x, y. Now consider the second quotient. Here x is fixed from the beginning, and y changes by delta y. As delta y tends to 0, this is exactly the definition of the partial derivative of f with respect to y at x, y. Therefore, the second quotient tends to partial f by partial y. The two remaining limits are familiar. Delta x divided by delta t tends to dx by dt by the derivative definition of x of t. Similarly, delta y divided by delta t tends to dy by dt by the derivative definition of y of t. All four required limits are now known. Finally, combine the four limits. We obtain du by dt equals partial f by partial x times dx by dt, plus partial f by partial y times dy by dt. The partial derivatives are evaluated at x equals phi of t and y equals psi of t. This is the two-variable chain rule, proved directly from the definition of a derivative. Let us remember the logic. First, convert u into a function of t. Second, apply the derivative definition. Third, name the changes delta x and delta y. Fourth, add and subtract f of x comma y plus delta y so that the total change separates into two one-variable changes. Fifth, prove directly that delta t tending to 0 forces delta x and delta y to tend to 0. Finally, divide and multiply by the proper increments, take the four limits, and combine them. Every step answers the demand created by the previous step.